Hello, my name is Nguyen, and the second author of this paper is Professor Jung. We are from Jung University, Korea. I'm here to present the paper, namely IECO-based approach on dynamic MSMD routing in the IoV environment in the IEEE Conference 2020. The contents of this presentation include the introduction, problem definition, and system model for dynamic traffic routing with the condition of multi-source, multi-destination traffic flow. Then we will show our proposal of the ACO-based routing approach. Next is the simulation, and finally is the conclusion of the paper. Internet of Things is a worldwide network paradigms that connect all the smart objects together based on the standard communication protocol. So each object can exchange information to each other. And a special case of the IoT in transportation is the Internet of Vehicle (IoV). They use the advanced communication technology like vehicle to everything communication to connect the vehicle with each other and various device at the roads, the infrastructure service, and the pedestrian with the mobile equipment. There is a research trend that how to make a vehicle can independently perform decision making and share information with each other to find a good solution. So in this paper we focus on the dynamic routing. We see the route set of dynamically select a sequence of route segments from origin to the endpoint of a trip. And colonial optimization ACO has been proposed to solve this problem and improve traffic flow in the many related work. But there are two main disadvantages of them. First, they consider the system is centrally, which require the huge computation cost. And secondly, they only investigate a traffic flow with a single source and single destination at a time. So the system cannot handle the multiple source and multiple destination at a time in the road network. First, I will give a short introduction about the ACO algorithm inspired by the forking behavior of the ant colony. So each ant will lay down a pheromone trail on the path when they move in from the nest to the food source, and more pheromone on the path will increase the probabilities of that path being followed by other ants. A sorted path is discovered via this pheromone trail. So this is the probability from the one node to another node when an ant consider a path for travel. And after complete the path, the pheromone value will be updated based on this function. With this pheromone value from each ant, so we present a dynamic traffic routing problem under the multi-source and multi-destination MSMD traffic flow condition, and we will report the correlating ACO-based methods to solve the problem in the distributed manner by coloring the vehicles beyond their destination, so we can distinguish the different traffic flow. And finally, we perform the simulation on NetLogo platform, the multi-agent platform, and show that the robust algorithm is superior in terms of two metrics. That's the average travel time and the number of vehicles complete their trip. Consider the graph. There is N naught and E S, which is N belong to big N represent a knot or intersection, and from one knot to another knot is the directed S that connect to knot, and its S have a distance Lig. A vehicle include identify the map, the action, and their source and destination. So the vehicle can have many different source and destination. So we call this character is the multi-source and multi-destination traffic flow. The problem is defined as follow. We'll minimize the travel time for the vehicle under the MSMD traffic flow condition. This is the indicator variable where the vehicle will choose the route segment Ig for travel, and TVIG represent the travel time taken by the V to complete the route segment. So to solve the multi-source and multi-destination issue, we robot the current N. So the current N's deposit the current Pokemon, and they only interact with that Pokemon. So the coloring vehicle with destination deposit the current Pokemon like this. So and they only interact with that Pokemon. It means that the route segment can have many Pokemon, but separately by the color of the vehicle with the different destination. By applying the ICO algorithm at a node or intersection, the vehicle will choose the next route for travel. By these probabilities, it compute by the Pokemon value and heuristic value over the total Pokemon value and heuristic value of the on the path that the vehicle can currently choose to travel next. We can see the Pokemon value represented by the tau lambda d Ig, which is the Pokemon value of the vehicle v lambda in I move to j at a time t, and eta Ig is the instantaneous state of traffic intensity on the route segment from I to j. Alpha beta indicate the related importance of the two values, and allow V is the set of the next route that the vehicle can currently to move next. When a vehicle choose the route segment Ij to move after they complete to travel on that route segment, they will update the performance value by this equation. In this equation, rho is the evaporation rate of the performance trails. The higher this value is, the performance trail will be evaporate more quickly, and the lambda tau IC is the amount of pheromone deposited by the vehicle while they passing. In this paper, the amount of pheromone deposited by the vehicle while passing the road segment not only based on the length of the road segment, but also depend on the travel time and the vehicle density of that segment. So there are three stages of the vehicle. First, it's entering, so the vehicle will enter the road segment. The moving state is the vehicle are moving on the road segment, and the existing state is the vehicle exit that road segment. So based on the this tree of state, we robust communication framework while the vehicle moving on the road, so it can exchange the information to compute the density of vehicle and the traffic intensity for the next segment. So here is the illustration of the process. When the vehicle entering the road segment, they will load the map segmentation, and while they moving, they can request the information from the other vehicle or the infrastructure of the road, and when they exit the road segment, they will send the global updates to update this information for other vehicle can use to make a decision making. This is the message function for the connected vehicle. That is request message. When they enter in the road segment, they will send the request message to get the information. And when they receive the request message, they use the local update message to send the information to the vehicle who requests the message. And then we assist the road segment, they will send a global update to update its information in the road sensor or other vehicle. We use the NetLogo for simulation. This is the multi-agent platform for simulating the interact between the agent. And we build the 2x2 risk scenario with A source and A destination. The vehicle will generate randomly, and the density of vehicle will increase from 5 to 50% versus for each simulation. Two methods are compared. First is the static-based routing methods. SP routing is the conventional static-based firing algorithm, so that discharge algorithm just based on the distance of the road. And the second approach is our robust method using the ICO, but we consider the multi-source and multi-destination at the same time, and The metric for evaluate those methods is the average travel time, which is the mean of travel time of on vehicle. The execute time is 100 ticks, and the second metric is number of vehicle. So given the 100 ticks, so which methods is process more vehicles is better. Here is the example of the simulation. We can see the characteristic of its source is 50%. And the average travel time can be get here, and number of vehicle can be get here. This is the simulation results. The density of vehicle will increase from 5% to 50% for each simulation, and we can see that the average traveling time of the ACO routing is better than the SP routing. The one reason is that the SP routing only consider the pack for travel, so it fixes pack. So when the vehicle density increase, there are more vehicle traveling the same pack, so it increase the chance to traffic congestion, and so the travel time will increase. In case of the ACO routing, it may find another pack that has lower density and lower travel time, that it know from the reverse vehicle travel to that pack, so it will reduce the traffic congestion, and the traveling time will be reduced. And we can see within the time of simulation 100 ticks, the number of vehicle of ACO routing can be processed complete their trip is higher, always higher than the certified routing. So in this paper, we propose self decision making for traffic routing in decentralized manner for the connected vehicle based on the improved ACO algorithm that consider multi-source and multi-destination traffic flow. So because of decentralized decision making, the vehicle need to communication each other to get information, so the communication framework also presented. So the simulation is conducted in the NetLogo, and we can see the robot approach can achieve better performance than the non-ACO approach.